Hey PChem peeps. So today we need to focus on determining pH and pOH and concentrations of H plus or OH minus of weak acids and bases. And that's essentially what we gotta do. What I want you to do first though is make sure that you look back at the answer key for this assignment and that you're feeling really comfortable with everything, especially figuring out pH, pOH, concentrations of H plus, OH minus, and going through the different ways of doing it. You have that little toolbox of relationships that can really help you determine what those are. These things are given on your reference sheet. These two are not given on your reference sheet. They are expected that you know how to undo a log, and this is how you do it. But check your calculations because some people end up typing on their calculator weird, and you gotta know how to do it. So make sure that you have gone through this and especially done something like 10 to the negative 1.5, because if you're not getting this answer, you need to know how to put it on your calculator. Okay? Also, these things are good to have memorized. These are things that you don't want to be looking up on your reference sheet because these are going to be routine and you are going to be using them. And we'll use them again today. But yeah, check over those. If you have questions, make sure you ask me or Mr. Mao. And that's number one. And number two is getting into dealing with weak acids and bases. Just kind of when we have dealt with weak acids and bases and comparing them how strong acids and bases work. Strong acids and bases completely dissociate, they go to completion, which means that the concentration of things like your H plus ion usually have equaled the concentration of your acid. And then the stoichiometry, or you can think of it as using stoichiometry or BCA tables in order to do that, but really you could kind of do this stuff in your head. And weak acids and bases, they don't completely dissociate. They're in equilibrium, and which means that the concentration of H plus you have to determine by using an equilibrium constant. We use constants like Ka, the A stands for acid, or Kb stands for base, but it's just an equilibrium constant like everything else that you have done. And using ice tables, it's like what you have already done. I'll kind of show you how to do that. But before we get into actually solving those out, a couple things we need to verify is that, and kind of review. When we talk about equilibrium expressions or equilibrium constants for acids or bases, the greater the equilibrium constant is, the greater the dissociation. So if you're talking about an acid, the greater the Ka, the greater the concentration of H plus. So when you're looking at strengths of acids, usually there's this, like I said, the larger the value of Ka, the stronger the acid or the more it dissociates, things like that. There's this other value, a pKa, which is a lot like a pH. The pKa is the negative log of the equilibrium constant, because P of equilibrium constant. And the pKa is often used in different areas, and a pKa kind of tells you the same thing. It tells you how much it will dissociate, but it's usually the lower the pKa means the more it will dissociate. You can almost think of it like a pH. The lower the pKa, the more acidic that it will be. The higher the pKa, the less acidic it will be. And these numbers can range by a lot. It's not confounded by between 1 and 14, but it does end up following a nice rule, especially with how it works with Kw. We'll get into that here later though. And so lower the pKa, stronger the acid. And then you can convert between pKa and Ka using these relationships. This is given to you, this is not. You need to know how to convert between those. Okay. So we're going to take a look at your practice for today. And off of this worksheet. You should have this worksheet, or you can follow along here and copy the problems down on a separate sheet of paper. That's fine. But it says it gives you three different acids with Ka values, which above is the strongest, and determine the pKa of each acid. I'm going to give you just a moment to try that out. All right, welcome back, you guys. So when we solve for which one's the strongest, we're looking for the one that has the highest Ka value or equilibrium constant, and that's this one. So HNO2, because it has the greatest equilibrium value or greatest Ka, and it dissociates the most. So now we're going to answer this question. Determine the pKa for each acid. To determine the pKa is equal to the negative log of the Ka value. So if we were to find the pKa for this one, it's the negative log of 4.9 times 10 to the negative 10th. And if I plug that into my handy dandy calculator, I end up with 9.31. So it's just like finding pH. When we say pKa, the equation is really the same as finding pH. We get this. You can check your other answers here by just waiting a moment. And there they are. So figuring out pKa, same way as we find pH. Also, pKa's don't have units. It's just a number. Sig figs follow the same rules. Okay? To undo a pKa, you need to be able to do that too. So it says the pKa of hypochlorous acid, HClO, is 7.54. Determine the Ka value of HClO. I want you to do that and then pop right back here in a second. Hold tight. And we get this. So something just to watch out for. Ka values, again, they don't have units either, so you don't need them. If you're ending up with times 10 to the negative 7th, something that you want to watch on your calculator is how you enter that in. This is really 1 times 10 to the negative pKa. So if you want to type in 1 times 10, that is okay. You could do that. Some people, when they use different functions on their calculator, if you type in 10 and then you're doing the EE button, that means 10 to times 10 to the whatever you put in after that. Make sure that you do 1 EE. And then type in the number. And that is 1 times 10 to the whatever power that you're talking about. And so yay, there we go. So time to change things up just a little bit. So when we're calculating pH of, this should say weak acids. And weak acids, we're going to go through this kind of groove. Usually we always start off with a balanced chemical equation. You have to have that. You always start with a balanced chemical equation. With strong acids and strong bases, it was pretty easy. We know that those go to completion, and we could estimate what those concentrations of H plus and OH minus could be. But with weak acids and bases, you have to use that chemical equation, an ICE table, and a Ka or Kb value. Again, when it's Ka, you're dealing with an acid, and that's all the A stands for. Kb, you're dealing with a base, and that's what the B stands for. And then we can go through and solve for the molarity, the pH, or whatever it is that we need. And we'll talk about these things here in a little bit. But this is kind of the steps you have to do and things that we want to remember when we're dealing with acids and bases. We always start with a balanced chemical equation. Strong acids go to completion, weak acids are in equilibrium, and then we can solve out for all our stuff. A lot of this is on your reference sheet, but like the things that deal with pH, all that stuff, our toolbox, are right here on your reference sheet. There are going to be some things that are not listed here. We'll talk about those tomorrow. And then what I want you to do is kind of write out those rules for how you deal with acids and bases on the side. So whip out your reference sheet, put that in, it'll be good. Okay? But we're going to take a look at some problems back on our assignment on how we go about doing it. We're going to do number 3 together, and then I'll let you do number 4. But here we goes. And So number 3, it says the pKa of hypochlorous acid is HClO is 7.54. What is the pH of a 0.100 molar solution of HClO? To solve this, I need to always start off with a balanced chemical equation. So I have HClO, aqueous. But because this is a weak acid, it is not one of our strong acids, I have to write out it's going to interact with water, and it's a reversible reaction. It will produce ClO minus and H3O plus. Because it's an acid, it will donate the H to our other substance, and here H2O will act as a base. So here's my balanced chemical equation. I can put in my other states, aqueous, aqueous. Great. That's what we start with. Then they told us the pKa. We need the Ka value. Good thing we did that in number 2. So here's our Ka value. But now to figure out the pH, I really need the concentration of H plus or H3O plus, and that's here at equilibrium, so which means I need to set up an ice table. I'm going to put in the information that I'm going to start with. Like here, when it says 0.100 molar HClO, that is the initial concentration of HClO. And we're going to assume that there is no ions that it has dissociated into yet. Because H2O is a liquid, I don't have to worry about it because pure liquids are not used in an equilibrium expression. So here's my setup. And now for the change. Because, or to reach equilibrium, I know that I'm going to end up producing products. I'm going to end up using up this reactants. So it's going to be minus X, plus X, and plus X. And then for at equilibrium, I just do the math. It's 0.100 minus X. And over here, I just end up with X and X, just like before. But I need, in order to figure out this pH, again, I need the concentration of the H plus or the H3O plus. And so what I need to do is really solve for X. All right? But I have to use my Ka value in order to do that. So I need to start by writing an equilibrium expression for this reaction. And it's products over reactants. So it's concentration of ClO minus times the concentration of H3O plus divided by the concentration of HClO. But these have to be at equilibrium. So I have to use the values down here. Then I can start relating everything together. 2.8 times 10 to the negative 8th, because that is the value of my Ka, equals the concentration of ClO minus at equilibrium was X, and H3O plus was X, and HClO minus, or sorry, HClO, not minus, was 0.100 minus X. Now there's some things that are kind of nice here, and we can check to make sure that we can fit in some assumptions, because this is times 10 to the negative 8th. That's much less than times 10 to the negative 4th. I can actually assume that everywhere where I have plus X or minus X, that those things are negligible. So I'm going to cross that out. And now I can solve for X pretty easily. I end up with X squared. On the top, I'm going to multiply this 0.1 over to the other side, and I will end up with 2.8 times 10 to the negative 9th. And then I solve for X. So hold on. All right. So once I solve out for that X value, I get 5.3 times 10 to the negative 5th. And that is equal to my concentration of H3O plus. That's what I want in order to calculate pH. So I kind of just worked out the rest of it here. The pH, it's the negative log of that concentration. And that's how I solve for the pH. So these problems, they do come back to the ice tables. You're going